Okay, so during this previous video, we basically discussed the simple clipping circuit like this. So we have diode and we have this kind of AC source. So this is your input, and we basically take the output across the diode. So then we found that there may be kind of a different clipping mechanisms. Either the output basically clip the input during this positive cycle, or once we change the orientation of the diode, we can move it to the negative cycle. And if we introduce multiple diodes in series, we can adjust this clipping level. And if you put this kind of arrangement like so two parallel diode with different orientation or the opposite orientation, we can basically clip both positive and negative cycles. So these are the stuff we discussed during this previous session. So this time we'll think of a different way. Like for example, now what happens is, so we know that, so if you have a diode, this is your input. If it is a kind of sinusoidal, so then this is minus and this is plus of the diode. So we basically found this kind of output. So if this is your input, so we found that the output would be something like that. So during this period, the output would be exactly equals to the new voltage of the diode, and rest of the durations the output basically follows the input. So then we build argument like once you introduce another diode like this, so this clipping point moves up to 2 times Vk. So if you add another diode parallelly, it moves to 3 times Vk kind of thing. So what happens if we introduce this kind, rather adding this series set of diode, what happens if we modify the circuit to this model? So we have a diode here. So then we have a fixed DC source here like VB. So this is the output and this is the input. This is your input, right? This is a resistor and this is the diode. Rather introducing multiple series resistors, so we basically add a kind of a bias voltage. So we basically add a kind of a bias voltage. So this is so we can think of it's a kind of a battery, a kind of a fixed DC voltage source. But the benefit of this one is like we can adjust this voltage according to our requirement. So this is a kind of a variable voltage, so we can, like, it's a kind of a power supply, so you can set it to 5 volt. If you want it to move it to 5.5, you can just raise it and keep it as it is. Like, it's a kind of a biasing voltage which we have a kind of a control over there to change the value of this VB. So see what happens to the output now. So how do you get the output? We can follow the same procedure which we discussed previously. So first we need to find the exact voltage across this diode. So if we mark the polarity of the diode, so this would be the actual voltage drop across the diode. So then we remove the diode from the circuit and find the, so this is V in, so this is your V open circuit. So if you apply the Kirchhoff voltage law for this one, due to this open circuit, there won't be any current flow through the resistor, so you can't see any drop across the resistor. So we can simply say that if you apply Kirchhoff voltage law, V open circuit plus VB equals to VI. So then the open circuit voltage equals to VI input minus the bias voltage. So from this we know that the actual voltage appear across the diode would be the difference between the input and the bias voltage. So to make this diode forward bias, what we can simply do, so if we assume that the diode follows a simplified model, okay, for the sake of simplicity, so we'll yeah anyway, so the so follows the simplified model. So then to make this diode forward bias, we know that the voltage drop across the diode should be greater than or equals to the knee voltage. So once you plug it to here, Vi minus Vb greater than or equals Vk. So then from this one we can build argument like the input should be greater than or equals Vb plus Vk. So this is the requirement that diode needs to meet. Diode needs to meet. So this is the condition that circuit needs to meet to make the diode forward bias. So we basically evaluate the actual voltage appear across the diode. So then we build an argument, or we build a kind of a condition that particular circuit should meet to make this diode forward bias. So this is the condition that particular circuit should meet to make it forward bias. Your input voltage is greater than or equals to the bias voltage plus the knee voltage. Okay, so then to make it reverse bias, so this should be the other, your input is less than your input is less than the base plus Vk. So these are the two conditions that particular circuit should meet to make this diode forward bias and reverse bias. So let's we draw the input circuit. So this is your input signal. So this is your input signal. Okay, so then we can mark this VB plus VK. So we can mark this VB plus VK. So let's assume this is your VB plus VK. So this is VB biasing voltage plus the knee voltage. So VB plus VK. So this is your input. So this is your input. V in. So by looking at this, we can clearly identify when and where this diode get forward pass. So one is like this. So during this portion, your input voltage is greater than VB plus VK. So your input voltage is greater than VB plus VK. So then during this block, we can simply claim that this particular diode gets forward bias. Okay. So what about for the other regions? So we can simply claim that our input is less than this VB plus VK, and that should be definitely reverse bias. And during this small block also that get reverse bias. Okay. Now, so we will basically evaluate the circuit for different so we can basically then evaluate the circuit for both forward bias scenario and reverse bias scenario. Okay, so we'll take the forward bias scenario. So we have a diode here. So we know that if it is forward bias, we have this, we can simply replace the diode with a fixed DC source of VK, and in addition we have this biasing voltage here, we have input voltage Vi also here. So this is the output voltage. So during this, so we know that the output voltage should be equals to, so if you connect a voltmeter here, you can basically measure the sum of these two voltages. So then the output would be VB plus VK. So this is for the forward bias scenario. So once it goes to the reverse region, so once it goes to reverse bias, so we know that this dot is reverse, so you don't see any dot here. So we can simply replace this with a open circuit element. So then once you connect your voltmeter to the circuit, so you can simply claim that your output would be equals to input. Once you connect a voltmeter here, so this is open, no current flow through the resistor, so you basically measure the input voltages. So then, so we can draw the output. So once this node is forward bias, the output would be VB plus VK. Otherwise, the output voltage is simply aligned with the V. So this is the V out for this. So now see, now the clipping level, is at VB plus VK. So if you change this VB, if you change this VB, you can adjust this clipping level. Like for example, let's assume we use the silicon diode. So then VK would be 0.7. So initially let's VB set it to 4.3. So then the clipping voltage, so we'll put CL. So it's the sum of these two, so 5 volt. So if you set the VB to 5.3, so then now the clipping level would be 6 volt. So likewise, by adjusting this clipping level, you can, by adjusting the bias voltage, you can simply change the clipping level as you wish. So then rather putting series set of diodes, you can introduce a kind of a variable DC source, and once you adjust the value of the variable DC source, you can simply adjust the clipping level of the diode. So if you want it to make it at 6 volt, you just set the biasing voltage to 5.3. If you make it to like 5 volt, you can set the biasing voltage to 4.3. So if you want it to set it to like 3 volt, you can put the biasing voltage to 2.3. So likewise, by adjusting the biasing voltage, you can simply get a different values for the clipping. So then rather introducing multiple diodes in series, you can introduce a kind of a variable DC source, and by changing the value of the DC source, you can adjust the clipping level. So this is, so you can adjust the limiting level, adjust the limiting or clipping level by adding a variable DC source. So this is the conclusion we can simply made out of this circuit. Okay, so yes, so we'll just go through the exercise number 4. Exercise number 4 for the clarification purposes. So now the circuit is this. So we have a diode here, we have biasing source, the value of the biasing source is 4 volt. So we basically take the output across this diode plus the DC source. So we have input. So input is not a sinusoidal, it's a kind of a triangle. Okay, so see what happens to the circuit for this particular input. So similarly, like in the previous, we can basically mark the polarities. So then, so this is the that voltage actually from minus to plus. So find the diode voltage. So we'll remove this diode for the moment and try to find the open circuit voltage. So by applying Kirchhoff voltage law, so we can simply say that VOC plus VI, so this is your input, should equals to 4 volt. Okay, so from this we can simply say that the open circuit voltage equals 4 minus VI. So this is the voltage apply across this diode. Ideally, like Vi is a kind of a triangular wave operate between plus 16 and minus 16. So the input should be like sometimes it's basically higher than the 4 volt and sometimes less than the 4 volt. So from this we can simply claim that to make this diode forward bias, what should do? So then the diode voltage should be greater than equal to 0. So here we can assume that diode is ideal. So this is the condition that diode needs to fulfill to make it forward bias. Once you plug it here, 4 minus Vi should be greater than or equal to 0. So from this Vi should be less than or equals to 4 to make it forward. So to make it reverse bias, so this should be the other way around. So if your input is greater than 4, that get reverse bias, keep in mind. So here the condition is slightly different. So to make this that reverse bias, you have to maintain your input above the 4. Once the input is less than 4, your that is forward bias. Less than 4, that is forward bias. So see, now this, if your input is less than 4, diode is forward bias, greater than 4, diode is reverse bias. So let's draw the input. Now we have this kind of a triangular signal. So this is plus 16, this is minus 16. So this is actually the input. Now the so from this, if so then by looking at this one, we can simply identify that the threshold or the limiting voltage would be 4 volt. So we'll mark this 4 volt here. So this is actually V equals 4 volt. So this is plus 4. So then we can clearly identify the regions where this diode is forward and reverse bias. From this we can say that if your input is greater than 4, your diode is reverse. So during this one, your input is greater than 4, then diode is reverse. Okay, so this is slightly different than the previous cases. So for the previous scenarios, what we found is during this block that get forward bias, but for this particular scenario that get reverse bias when your input is greater than 4, because the diode's orientation is the other way. So once your input is less than 4, diode get forward bias. So during these blocks, diode get forward bias, and during this as well, that get forward bias. Okay, now we basically identify the regions where this diode is forward and reverse bias. Now this is the time to find the output voltage. So see what happens if the diode is forward bias. So we know that diode is forward bias. Let's start with reverse bias, then it's easy for to identify. So to make it reverse bias, so once this diode is reverse bias, this is open. So then the circuit is something like that. Here you have open circuit, and here you have a source of 4 volt, and R, this is your input. So then what about the output? So V out basically should be equals to V in. So once this diode is reverse bias, your output should equals to Vi, because this is open. So then there are no current flow through this one. I equals 0. So you basically measure V out as V in. input voltage becomes the output voltage. So what happens if it is reverse forward bias? So you have circuit here, so you have source, sorry, uh, so this is the ideal diode. So this, then if it is forward bias, this is short circuit, and you have 4 volt here, so you have input, you have resistor. So what about your output? So you are measuring output as a 4 volt. So this is the, so you just connect your voltmeter across this 4 volt DC source, so then the output would be all the time it's 4. So then we'll try to draw the output on top of this input and this. So we know that during this is the input voltage. If the input is greater than 4 volt, that get reverse bias, and during this reverse bias region, your output should be Vi. So this basically align with the input voltage. Okay. So once this start forward bias, your output remains at 4. So it means this. So this is your output. Okay. So this is one exercise. We can demonstrate this clipping, but keep in mind, so we don't need to stick into the sinusoid. We can have different type of random signals. So this is a one example to try out. So this, in this case, your input signal would be a kind of a triangular wave. So we can have the square wave, we can have a kind of random periodic signals. So the common signal is a sinusoid. So you should be able to get this output for any kind of a input signal, any kind of a diode orientation, any kind of a voltage, biasing voltage. So we can change the polarity of the biasing voltage, we can change the orientation of the diode, we can change the um, uh, the resistor. I mean, like, we can push this resistor to the this branch, so we can put this resistor here and diode and the sources like here. So we can have different combination. At the same time, we can change the input voltage as well. So you should be able to properly analyze the circuit in any kind of a variation. So you can have multiple sub scenarios. So you should be able to manage with this basics to get the output for any kind of a scenario. So then okay, so we will discuss one more examples to clarify some special things. Okay, so we'll move to exercise 2. So the first circuit is very straightforward. If the diode is ideal, you know that it's a kind of a half wave rectified version. So the in the positive cycle should be there in the circuit. So if you want, so you can try this. So I have diode here. So keep in mind, so this is minus, this is plus, this is your input, and this is your output. So keep these, so we'll put these pluses and minus for this input and output. So this is the notations we stick into, like this terminal would be a positive polarity, this should be a negative. So once you get a negative value, so it means like the polarity should be reversed. Like otherwise we cannot draw a graph. So for the moment we stick into the sign convention. Your input are like this, plus and minus. Your output also mark as it is, like this terminal is plus and this terminal is minus. So if you get a negative voltage, so you can reverse the polarity. Here also see, like if you have kind of a sinusoidal signal like this, So this is treated as plus and this is treated as minus. So in during this block we'll mark the voltage to the upward. So during this you have a kind of a negative voltage, so then we can mark the voltage like this become minus and this become plus. Okay, so that's why we stick into the sign convention. So your input and output voltages are marked like that, so the polarities are marked like that. So if you have a negative voltage, so you can draw to the negative direction with respect to the sign convention. We stick it to here. So here plus here minus means if you get a negative voltage, so definitely it to be like this. So for this particular circuit, so you can easily find that. So the diode voltage is something like that. So you can simply say that once you apply Kirchhoff voltage law for this direction, Vi plus Vd or the open circuit voltage. So we'll put OC for the moment, C equal to 0. So then VOC is actually minus Vi. So then the drop would be like minus Vi. So to make it forward bias, we know that Vd should be greater than or equal to 0. Once you plug it to here, minus Vi greater than 0. Once you remove this minus sign, this is actually this. Okay. So to make this diode forward bias, your voltage, input voltage should be less than 0. So to make it forward reverse bias, so we can simply say that your input. So these are the two conditions. So if you draw it, so this is your input. Okay. So this is your input and Vi greater than 0 means during this block your diode is reverse bias. During this block your diode is forward bias. So once this diode is forward bias, we can replace the diode with a short circuit element and V out would be 0 because so this is short then, so V out is 0. So during this forward region your output is 0. If it is reverse, you can simply replace the diode with open circuit element. So then if it is open, there won't be any current flow through the resistor and your V out should be simply V in. V out is 0. During this V out is V in. So this is your V out. So with this diode arrangement, you will get this kind of a signal. So you will simply get the positive cycle appear at the output voltage. So what about if we change the circuit to this? So we'll add a source here. This is your input and you have another source, diode, resistor, and this is your out. See what happens to the circuit then. Okay, so this is the polarities of the diode. So this is the voltage drop across the diode. So do this. So we'll find the actual voltage find the VD, actual voltage across the diode. So we'll remove the diode first and apply the Kirchhoff voltage to measure the open circuit voltage. So we can simply say that Vi plus the source voltage V minus Vd equals 0, because once you remove the diode, this is the circuit is simply open, so there won't be any current flow through the resistor. So then you can read the sources only. So Vi plus V should equals to Vd. So from this one we can simply say that Vd will put open circuit voltage for the clarity. So this open circuit voltage, so the open circuit voltage is actually Vi plus V. So then this is the actual voltage appear across the diode, which is equals to Vi plus V. Okay. So then to make this diode forward bias, we know that if it is ideal diode, this should be greater than 0. So by looking at this one, we can simply claim that your input plus V should be greater than or equals to 0 to make it forward bias. To make it reverse bias, Vi plus V should be less than 0. So these are the two conditions that particular circuit needs to satisfy to make this diode forward and reverse. Okay, then we'll try to draw this one. So this is your input. So this is your input. But by looking at these two statements, so we know that the switching of the diode is depends on the Vi plus V, not just the input voltage. So the clipping is basically, or switching is basically happens with respect to the Vi plus V, not the Vi. So then the easiest way is like we can draw this one. So then easily identify the regions where this Vi plus V is greater than 0 and less than 0. So let's assume V is a kind of a positive quantity. So then this should be like this. So this is simply uplifted by V unit. Okay. So then it's something like that. This one. So this is actually Vi plus V. So then from this we can clearly identify the switching region. So this is the region where your input is greater than 0. So once your input is greater than 0, this is forward bias, and during this block your input plus V is less than 0, so it should be reverse bias. During this again forward bias. Okay. So if the diode is forward bias, so this is short circuit now. So then what about V out? V out should be, if this is short circuit, so your output is Vi plus V. For this scenario, V out, so this is open because your diode is reverse bias. You can replace the diode with open circuit voltage. So then basically you simply isolate the sources from the output. So V out would be 0. So this is open. So then V out should be 0. So this is open. See? So V out is 0. So then based on this we can draw the input. When it's forward bias, your output follows your Vi plus V. Once this diode reverse bias, your output is 0. During this block it's 0. So rest, it's just follow this Vi plus V, not Vi plus V. So then this is the output. Okay, so hope this exercises and the examples and the theories are clear. So if you have any questions, just drop a message to the discussion forum or write an email.